Hello, this is Nitin Dahad with the Times. I'm talking to Russell Hager, who's the founder and chief executive of a company called VyperCore. Russell, hello.
Hello, Nitin. Good to see you again.
Good to see you. We met a couple of years ago. You came up to see me when you were just a bit before your seed funding, or just around the time of the seed funding. Tell us about VyperCore and what you're doing, because I think it'd be interesting just to get some background before you tell us the news that you're announcing.
Sure. So VyperCore, we started 2 years ago when we saw you before. We were then just me and my co-founder Ed, and we're now up to 17 people based here in the UK, Cambridge and Bristol. We are doing a new processor. So it's a technology that's come out of university. The technology can be applied to any processor architecture, general purpose processor architecture. You like CPUs, not GPUs. We're essentially doing for general purpose compute what GPUs have done for AI. The difference being that GPUs and processors for AI generally it's been going for quite a while. There's a lot of advances. At the same time, CPUs are basically doing now what they did 40 years ago. Very little architectural change, and we've seen that in the complete tail off in performance in the industry.
Traditional von Neumann.
Exactly that. It's a cached architecture, processor pipelines. Nothing's really new. We've got more transistors on a die, more cores, but actually performance increase in general purpose processors is shrunk down to about 3% or 4% per year. And what we're offering is a step change up to 5x, 400% improvement.
Okay.
Without changing your code. That's the key thing. It's not a new architecture, it's not a new language. It allows you to take your existing code base and just redeploy it and get all that benefit.
And part of what I remember from our conversation a couple of years ago is what's called memory garbage collection. Basically, you're getting rid of memory that's sitting in there which doesn't need to be there.
Yeah.
Contents of the memory.
That's right. So when you're running an application, unless you're a computer scientist, you just don't really think about what's going on under the hood inside the software. But if you're writing code in Python, there's background software that's keeping track. This bit of memory has been allocated to that bit of code. It's not being used anymore. Free it up. And what's not really that well understood is the amount of time overhead, the amount of CPU effort that's going into keeping track of all of that. And what we've showed is that the overhead it's about twice as much as the industry expected it to be. It's up to 80% of the CPU's time is spent keeping track of all that allocation, freeing, identifying what needs to be freed up. And we take all of that out of that background software. You don't change your application, it comes out of the background software. We embed it inside the CPU in a way that it runs in the background to the CPU. So what we have is a whole CPU design, but the technology is running there in the background, and basically all of that 80%, and it varies by application, so it's up to 80%. All of that 80% is freed back to the task, and that gives you the 5x performance improvement without changing your code.
Okay, and I mean, not to go into detail, probably viewers can't see this here, but we did a test demo here. Just run us through what that showed us.
Yep, so this is a platform that we're actually launching. So it's our cloud-based evaluation platform. What we're showing here is, so this isn't aimed at chip people, this is aimed at data center users, people that are deploying code in the data center. So they're writing their code in C# or Python or Java. This is a Python-based demo. We've got a Jupyter notebook, which will make sense to people that know about deploying Python. And what they're able to do here is they take existing code they're already running in production, live code. They deploy it on the notebook here, and we're running a full FPGA build of our processor architecture. They'll run it once on the FPGA inside the cloud, and they'll run it again on a vanilla processor platform. And the technology will then say side by side, it will give you X times more performance. So it allows our early adopter partners to come along, and the ones who are keen to see what's coming next. So this is, as a chip, it's still some way down the line, but people want to see what's coming what's coming next. 4% performance increase right now is not very exciting. 400% really is exciting. Try your code out, prove that you can deploy it without changing the code, and see how much faster it's going to be.
So this is running on an Amazon Web Service, AWS F1?
Yes.
Okay.
Right. Yep.
And so you've got your processor instantiation there, FPGA in an FPGA. Is that right?
Yeah. So the AWS F1 is an FPGA instance. It's a server class FPGA, so you can run full-blown server class processors and server class workloads on it. So people that are already running software in the data center, they can deploy they just redeploy. They don't change a line of code. It's not about porting. It's just a DevOps task to redeploy on that. We've got a full build of the processor inside that FPGA.
Okay.
And
that's the RTL running in there.
That's right. So it's full RTL, and that allows people. We're essentially counting cycles when they're running the Python code on a vanilla version. We're counting how many CPU cycles, and then they're running on our processor, and we count CPU cycles. And it's this very simple ratio of how many cycles versus how many cycles. That gives you the 3x, 4x, 5x.
And so somebody who's used to doing Python and whatever, they'll see the difference straight away, or do you help them in any way to understand some of that data?
They'll be very familiar with Jupyter. So we're giving a development environment they already know and love, hopefully.
Yeah.
And so this might not be something that chip people fully get, but it's what the Python community would fully get. And they'll play with this, and we're getting a bunch of metrics out of it. So we never see their code. One of the beauties of it being on the cloud is, a lot of people are very cautious about sharing code with third parties. They can fire up this instance in the cloud, run their code. We don't have to see it. They just give us the results. They give us a bunch of numerical results that come out, which allow us to do the comparison, and that's all we see.
Okay.
And they get to play with some cool technology that's going to be available to give them acceleration down the line.
Right. So what you're launching is a evaluation platform on the cloud, which is this, and so you're encouraging what you call lead partners to come and try it. Is that right?
That's right. So this is something, you come to our website, you can register to be engaged in the lead partner program. And then you get access to the F1 instance, and then you do it by yourself. We don't get involved, we're not seeing anything. The performance is just one part of what we do. There's three aspects to what the technology delivers. We're kind of interlinked. So that 5x performance is also about power consumption. You can look at it either that for the same amount of silicon you get 5 times more performance, or if you actually, for a given amount of performance, is potentially 5 times less silicon, which is essentially 5 times less power.
Yeah.
So there's potential here to look at it as a major way of saving energy consumption in the data center, which is a really big topic right now. Everyone's really focused on the AI data center energy consumption, and actually there's a much bigger energy consumption problem coming from general purpose compute as general purpose data centers get rolled out as well. And actually there is no step change available. This is the only one that we're aware of to save power consumption of that. So there's the power consumption as well as the energy, as well as performance saving. There's also a related issue, which is memory safety.
Yeah.
So memory safety at hardware level is an increasingly hot topic in the industry. It's, with people talk about Rust as a software-based solution, and it definitely has its place. There are other hardware-based solutions out there which all have their place. We're not directly competing with any of these stuff. There's multiple ways to solve this problem. Our technology as a processor is fundamentally memory safe. It's as simple as that. And people can also start to use this platform to evaluate the memory safety as well.
Okay, so summarize, you've got an evaluation platform, you want customers to try it. Who are the customers?
The customers are people using
or partners rather.
Yeah, it's people who are deploying code in the data center. I mean, ultimately we're selling chips, but we're selling chips into an ecosystem. The end user is someone who's already deploying a server class workload in a cloud data center, in a private data center, in a server somewhere. Typically the sort of application which is deploying onto many servers at scale, so a cloud, a web-based delivery.
Okay.
Those are the end users and ultimately will be our customers.
So people like financial markets and all that. Yeah.
Financial markets, web enterprises, data processing businesses.
Which is kind of where like Xilinx were targeting a lot with the original launches of things like Vertex and all that.
Yes.
Yeah. Okay.
Exactly that. I mean, the difference is the whole GPU market, the FPGA market, they've required people to rewrite their code from scratch with a completely different paradigm, which is great because that's how those technologies were able to advance. We're coming along and going to a community that's not based around computer science or electronics engineering, and saying your existing code, just redeploy it. It's just going to work.
Now, you raised, I think, 4 million the last round, the seed round. You're going to be raising more. I guess, what is it you're delivering to customers? And that's kind of still 2 or 3 years out in terms of silicon, but what are the expectations from your lead partners right now?
Yeah, so we're building a processor takes time. I always say to investors, if you're looking at the universe of semiconductor investing, then processors at the expensive end, but actually we're at the cheap end of processors because our customers have already written the code that's going to run. Most processor startups have to raise a lot of money because there's a whole software ecosystem to build. So our customers have already written the code. That's the easy bit. It'll take a while. We're looking at having commercial silicon available 3 years from now. We've got to go through a funding round or two to get there. We're looking at having test silicon available realistically start of 2026, Q2 2026.
And you've done lots of things like being part of things like Silicon Catalyst and various programs, which gives you access to some of that early silicon as well.
We benefited from, we were on Intel Ignite program, which is really helpful to us, and also Silicon Catalyst, which is an ongoing program. We're really big fans of that. Gives us access to a whole bunch of what they call in-kind partner benefits. And we'll be doing the MPW through that program as well. That's where the test chip will come from.
Okay. So, what's next? Fundraising, I guess.
We're in
after
fundraising
this.
mode. We're doing the biggest thing really for us as an organisation is the team growth. We're 17 people today. We're a very small team. To have achieved a clean sheet 64-bit processor architecture from scratch in what's basically been 12 months is a huge achievement for the team as a whole. We're going to be expanding that team. It's some of the most exciting processor engineering, I think, in Europe at the moment. So we'll be doubling the size of the team, more than that actually. Once with the funding in place, obviously, we've got a huge amount of engineering to do across processor architecture, memory architecture, software development, supporting the tool chain and the runtime, a whole bunch of really interesting stuff. And from the engineer's perspective, what's really exciting is it all meshes together. We talk about hardware, software, co-design. This is kind of one step beyond that. It's just fully holistic design. Everything's designed in lockstep, but in a way that the customer doesn't notice because their code just works.
And your background is silicon. A lot of people, I think, you've had a good sort of journey in that industry, haven't you? So
I've been busy. I've been involved with. I started off doing connectivity, hardware, silicon, and hardware back in the 90s and 2000s. Pretty much everything I've done has either been connectivity or compute. In that time frame.
And I think if I remember, and you can read this on the Times from last time we interviewed, but you've got some sort of amazing sort of people behind you as well, like David May and all that. Originally.
So the technology here has been effectively 12 years in the making. It's gone through the entire academic environment and really benefited from the know-how. This is deep computer science meets deep processor architecture. And we've got the team we've got is really experienced. My co-founder Ed, who's really the progenitor of all the idea, he's done it from a deep computer science perspective, but in a way which is industry relevant, not just purely academic. So it's got this brilliant combination of these different elements.
Well, Russell, thank you very much and good luck.
Thank you very much. Really good to see you again.
Thank you.
Bye.